Okay, so we're going to review accuracy and precision. So you saw the video that I just showed you a few minutes ago. So you got some kind of idea about what accuracy and precision is. So let's review the definitions. So accuracy is how close a measurement is to the actual or true value. We'll put actual value. Precision is how close a measurement is to other measurements. So, other measurements. Oh, let me clean that up. So, other measurements. Okay, so you're basically, when you're talking about precision, you're doing a comparison of how close one measurement is to other measurements that you did in an experiment. Okay, so let's move on. So if we look at this example here, precision versus accuracy. It says look at each target and decide whether the hits are accurate, precise, neither, or both. Alright, so if we look at A, we see that all these darts are scattered throughout the whole target. So we would say that they are not accurate because they don't hit the bullseye. So not accurate. And if you see the bullseyes are scattered, they don't concentrate in one particular place, so they're not very precise either. Not precise. Okay, example B. Here, you notice that all the darts hit the bullseye. The bullseye represents accuracy. So all the darts hit the bullseye. You would say that those measurements, if we're talking about measurements, yes, they're accurate because they hit the bullseye. And they're all concentrated in one particular spot, so they could say like those measurements are close together. There's not a big difference. So yes, they're precise. Example C, again you see the darts are scattered throughout the whole target. So again, they're not accurate because they don't hit the bullseye, and they're not precise because they're not close together, they're not grouped close together. So again, not accurate and not precise. Alright, now looking at example D, well, none of those darts again, they don't hit the bullseye, so they're not accurate. But if you notice, they are focused in a particular area here, like the lower left-hand corner, even though it's a circle. So they are focused in a particular region. They're all more or less focused in this region here. So even though they're not accurate, they are precise. So hopefully this gives you some idea as to how you tell whether a measurement is accurate or precise. Okay, we're going to move on and do a few examples. Okay, so precision problem number 1. So precision problem number 1 says a group of students worked in separate teams to measure the length of an object. Here are their data. Team 1, okay, you have 6 teams. Each of them took the length of an object and they came up with these measurements. Okay, so if you look at all these measurements, they're all pretty close together. There's not a big difference in these measurements. So they're pretty precise. We're going to go through these series of questions to figure out how precise. So you have the average length in centimeters. Okay, so you're going to calculate the mean. So to do that, you add the 6 measurements here, the 6 pieces of data, and then you divide by 6. That gives you 2.70 centimeters. Okay, this is the mean or average. Next, it says subtract the highest value from the lowest value. And this is going to give you the range or the spread. So here's the highest value, and here's the lowest value. So when you subtract the 2, it gives you a value of 0.20. Okay, so this is the range. And now it says to divide by 2. When you divide by 2, this is going to give you the approximate range from the average. So 0.2 divided by 2 gives you 0.1. Okay, next you go on to question number 4. It says the precision of the measurements can be shown as an average range. So the precision of the measurement was 2.70, and then the range, or the average of the range, is 0.1. All right, so this is how we calculate precision. Okay, again, looking at the average and comparing to all of these measurements of data, you know, they're precise. They're pretty precise. There's not a big variation in these measurements. And as we go through all of these, going through the whole calculation, we see that it varies by about 1/10 of a centimeter on average. So there's for example number 1. Let's try example number 2. So in example number 2, it says a second group of students obtained the following data. So it's a very similar example to problem 1, just slightly different data, and the instructions are sort of abbreviated, they're shortened. So on the average length of these 4 pieces of data is, according to my calculations, 2.69. So I added and divided by 6. The precision. Okay, so we have to find the range. So we take the highest value, which is 2.8. We take the lowest value, which again is 2.60. Subtract the 2, that gives us 0.2. And then divide by 2, that gives us 0.1. So when we come up with this summary of our precision, you're going to write the average, 2.69, and then plus or minus, which turns out again to be 0.1. So, in case you kind of got lost there, it's 2.80 minus 2.60 gives us 0.2, and then we divide by 2, and that gave us 0.1. And that's how we came up with the plus or minus. So this represents our precision. Again, most of these values are pretty close together, and they're close enough to where they're about 1/10 of a centimeter apart. Overall, pretty precise. Now, if we compare the problem number 1 with problem number 2, let's see how the precision compares. So go back, look at problem 1. Okay, 2.7 plus or minus 0.1 centimeters. compared to 2.69 plus or minus 0.1 centimeters. So question 3, it says in comparing groups, the first or the second, which was more precise, or was the precision the same? Justify your answer. Okay. The precision the precision was pretty similar, since there was only a 1/10 of a centimeter, which is kind of like your margin of error. I would say the precision is very, very similar. They're not exactly the same, but they're very similar. I think that's a good enough answer for our purposes here, where we're just trying to introduce precision and accuracy. So we'll say that precision was very similar, or very closely related. And that'll answer question 3 in problem 2. One last thing that we have to look at is percent error. Okay, so here's the next piece of this lesson, expressing errors in measurement. So now we're going to learn how to calculate percent error. Best way to do that, I think, is with an example. So it says scientists often express their uncertainty and error in measurement by giving a percent error. The percent error is defined as percent error equals actual value minus theoretical value divided by the actual value, and then you change that to a percent by multiplying by 100. So the actual value is basically the number that you get in your experiment. So these are your results, or your data. That's where you get the actual value. Theoretical value is either given to you by your teacher, or you can look it up. Okay, so we will say it's given. Okay, so now we can look at this example, read it, find out what's the actual value and what's the theoretical value, and we can calculate percent error. So let's do that. It says, answer the following questions. There's only one question, but we're answering the following question. While doing the lab, a student found the density of a piece of pure aluminum to be 2.85 grams per cubic centimeter. The accepted value for the density of aluminum is 2.7 grams per cubic centimeter. What is the student's percent error? Okay, so if we look at this, okay, it says a student found the density of copper to be 2.85 times 10, or 2.85 grams per cubic centimeter. So this is our data. So that's the actual value. It says the accepted value for the density of aluminum is this. This is going to be the theoretical. Okay, so now using these two numbers, we can calculate the percent error. So let's do that. Percent error. All right, so it's going to be the actual value, which is 2.85, minus a theoretical value, which is 2.7, divided by the actual value, which is 2.85. Okay, when you subtract the top, you get 0.15. And then you divide that by the bottom, 2.85. Then you divide that and you multiply by 100. Multiplying by 100 converts it to a percent. This will be the percent error. So let's see what we get here. 0.15 divided by 2.85 times 100, 5.26%. And this is the percent error. Okay, so I hope that this mini lesson here helped us to learn the difference between accuracy and precision. Hope it showed us how to recognize it in sample problems or examples that we may run into. And hopefully this was a good introduction to calculating percent error, because we'll be doing a lot of this in our labs later on in the year. All right, see you next time.